Today is Monday, May 14th, 2012. This morning, what we did when we started class was we checked our Charles Law, our Gay-Lussac's Law. The answer key on that's on my blog, so you can check that. Basically, today what we did is we first discussed why we've got to use Kelvin temperatures with gas laws. We also, and it's not actually written down here, we also talked about the combined gas law and how to use that to solve problems. Tomorrow we're going to talk about the ideal gas law. Wednesday we're going to talk about kinetic molecular theory and also solve some mixed problems. Now you can read ahead in your book about the kinetic molecular theory. That would help out the lecture quite a bit. All right, here we go. So the very first thing, why do we use Kelvin temperatures? Well, let me just show you this little diagram here. It basically talks about how Lord Kelvin originally came upon negative 273.15 degrees Kelvin. Actually, he came around negative 270 degrees. We've refined that since then. Basically, here's the idea. If you make a graph of pressure versus temperature, what you're going to find out if you do some experimentation is you're going to find out that as a gas lowers in temperature, you're going to find that the pressure decreases and decreases and decreases. And as this graph goes down, and we extend this graph down, we understand what a negative temperature is, but we really don't understand what a negative pressure is. So there's no such thing as negative pressure. As we continue to go down and down and down, you're going to reach this x-axis. And right here where it meets the x-axis, at this particular point there, that's where reality meets, I don't know what it is, something artificial, an artificial construct. In the real world, these two quadrants down here, it would be quadrant 3 and quadrant 4. In the real world, quadrants 3 and 4 have no meaning as far as a pressure-temperature graph is concerned. So Lord Kelvin decided that what this means is that there is an absolute temperature at which things can get the coldest. It turns out that the x-intercept on that is negative 273.15 degrees Celsius. He calls this absolute zero, so we call it absolute zero also. We call it 0 degrees Kelvin. Okay. Now, just as kind of a reminder, why is it that we don't use another way to put this? Why is it we don't use temperature scales that can be negative in a gas law problem? Well, here's another good example. Let's say that I have exactly a 1 liter container and that it's at room temperature, which is somewhere around 26 degrees Celsius. Notice I'm using the wrong temperature scale on purpose here. The question is going to be, what should the volume be if I chill this 1 liter of gas out? So I take the 1 liter container and I toss it in the freezer. My freezer, I'm going to say, for the sake of making the math easy, is going to be around negative 13 degrees Celsius. Now, we all know that as the gas gets colder, that volume should shrink, so I should have a much lower volume than what I had before. We solve for the math. Negative 13 times 1, well, that's negative 13. 26 times v, well, that's 26v. Divide both sides by 26 so that I can solve for v. And v winds up being, got to carry that negative sign down, 0.5. And the units on this, well, I had liters, so I should have liters here for volume. So I get negative 0.5 liters for volume. Hold on. Negative liters? That makes absolutely no sense. Why does it make sense? Because it make no sense? It's got a negative sign. And the reason why it's got a negative sign is because we're using a temperature scale that allows for negatives. That's why we use the Kelvin scale, is so that we have absolute temperatures that are absolute values. They're not negative. So in summary, don't use Celsius, don't use Fahrenheit. Use Kelvin for all gas law problems. Otherwise, you're going to get a nonsensical answer. Okay. Today's notes aren't that difficult. Mostly it's a little memorization of stuff. One of the things that we reveal is that STP stands for standard temperature and pressure. Occasionally we've seen chemistry problems that say assume standard temperature and pressure conditions or assume STP, and we've been asking, what does that mean? What does that mean? This is exactly what it means. When a gas is subjected to different temperatures and different pressures, it takes up different amounts of volume. So scientists have come up with a standard to deal with that. The standard is exactly 1.00 atmospheres. If you need to think about that, if you need a mental image for it, think about a nice day at the beach, not Lake Michigan Beach, but the ocean. If you're standing on the ocean, at the ocean on an average day, you've got exactly 1 atmosphere of Earth above you. Up here in Chicago, we're 950-ish feet above sea level, so we have less than an atmosphere above us. So when a temperature says it's STP, that's exactly what it means. Now, it means standard pressure is 1. Standard temperature, the T part, is 0.00 degrees Celsius. So think about a really, really cold day on the beach. The water is freezing. Okay. Matter of fact, a glass of water is going to be equilibrating between being frozen, solid, and being liquid. Because we know that liquid water and solid water exist both at that same temperature, 0.00 degrees. That's about all I need to say about that. Please memorize that. That way, if I give you a problem that says that it's at STP, you know it's 1 atmosphere in 0 degrees Celsius. These items, these two bullets here, don't bother memorizing it. That'll be on the test. You just know how to use it. You just have to know how to use it. All right. Now, it's been years since I've had to derive this law, so I'm not going to derive it here. But basically, if you look carefully, what you'll see here is you'll see Boyle's Law right there. You'll also see Avogadro's law right here, volume over number of moles. Now, if we look carefully here, pressure versus temperature and volume versus temperature are Charles and Gay-Lussac. So the orientation of where these variables are is exactly the same as it was in the four separate laws. It's just that now we've separated them out. So I'm going to erase these items here. Why do we use this equation? Why is this important to add all these laws up? Well, it's realistic. Typically, we don't see we don't see situations where only 2 variables are being changed at a time. Typically, we see realistic situations where the number of moles, the temperature, the volume, and the pressure can all change at the same time. So we need an equation like this to deal with realistic situations. Again, we've got before and we've got after. Again, there's no specific units necessary except for temperatures. Temperatures must be in Kelvin. And then the other issue is the same issue as it was for the other gas laws. Volumes have to be in the same units. So if one of them is in milliliters, the other has to be in milliliters. And pressures also have to be in the same units. So if one is in atmospheres and one is kilopascals, you're going to have to convert so that they both match. Number of moles and number of moles, well, there's no other way to write number of moles besides in moles. So if it's not in moles, you've got to convert to moles. Okay. I think that's pretty much all that we really need to do here. I can show you this problem here. A balloon is filled to a volume of 7 times 10 to the second milliliters, 20 degrees. The balloon is then cooled at constant pressure to a temperature of 1 times 10 to the second Kelvin. What is the final volume of the balloon? Notice both pressure and number of moles are constants. So if I'm going to try and solve this one, I'll just kind of set it up for you. P1V1 equals N1T1. P2V2 equals N2T2. Now, if I've got to take a look at this, they tell me initially that I've got 700 milliliters. And they also tell me that it's at 20 degrees Celsius. So I'm going to write down 293.15 Kelvin. I just converted that in my head. 273.15 plus 20. They also tell me what is the volume, and they tell me that its temperature is going to be 100 degrees Kelvin. I don't know what the pressure is, and I don't know how many moles I've got. If I don't know how many moles I've got, that's pretty simple. I'm going to make up a simple number that is not going to affect the math. Notice if I multiply by 1, nothing happens. If I divide by 1, nothing happens. All right. Pressure is going to be the same story. I'm going to make up a simple number that won't change anything. Notice one pressure units, whether that's atmospheres, kilopascals, or millimeters of mercury, doesn't really matter. It's exactly the same as this unit, 1 unit of pressure. I can't put in different units. The easiest thing to do is just make up 1. Why do I make up 1? Well, I want to make my math easy. 1 times 700 times 1 times 100, well, that's only 70,000. And then 1 times 293.15 times 1 times v, well, that's 293.15 times v. Notice the math got really simple because I took the things that didn't change and I made them simply 1. Dividing both sides by 293.15, and I'm going to find out that the volume should be equal to 239. What units do I use? Well, the same volume units I used before, milliliters. That's it for today. Quick and simple lesson. What you want to do for homework is you want to work on the combined gas law worksheet.